sort of talking session of the boot camp is more speed talks. And we are happy to kick it off with Alex Grillo from Lip6, I guess. We just had a discussion about why that is the name, telling us about cryptographic applications of quantum error correcting codes. Go for it.
So yeah, this is not a talk where I'm talking about like exciting new results. It's more to give an overview where quantum codes can be used on top of everything that you have seen so far. And just to start with it, oops. So let's give a step back and talk a bit about quantum and crypto. And yeah, I think the first, quantum got a lot of attention when actually people realized that quantum helps malicious parties. So then we have to come up with new assumptions that are quantum resistant. And this is one way of code, also to connect codes with quantum is try to find a new post-quantum cryptographic cryptographic assumptions. But the good thing is that quantum also helps honest parties. So you can use quantum resources to achieve new cryptography. And this is the focus of my talk, how to do new cryptography, but now sending qubits over a quantum channel. And yeah, as I said, I want to talk very generally how quantum codes can help to build cryptographic primitives. And I'll talk about a lot of old results and a few new results. Yeah, the idea is to keep it very, light. It will be a brief overview of everything. And I'm happy to discuss things later if people are interested. So let's dive into the first applications. Is about authentication. So the quantum authentication is how can Alice send a quantum message to Bob, and Bob is sure that he received a message from Alice and nobody tampered with that quantum message. So what we want is that Bob, when he receives this message that's encoded by Alice, that he decides that someone tampered with it or it was the original message. Briefly, okay, yeah, maybe it will be too many details, but the idea is that quantum codes allow us to do that. So we assume here, for example, that Alice and Bob, they share some common key, and this allows them to authenticate quantum messages as well. And actually, this is not really quantum, so the same classical analog also works. It's just an example of things that do quantize, like how quantum codes, they have the same behavior as classical codes when you're in the classical level. And how does this scheme work? So as I said, they share a key. And we see the key as some bases. So like all these 0-1 bases or the Hadamard bases, like the plus-minus bases. And they share a bunch of random bits that I call here A, B, and X. And they also share a random permutation on 2 lambda qubits. And the idea of the encoding is the following. So first, Alice will encode her quantum state using a quantum error correcting code, and then apply the quantum version of one-time pad. So she will fully hide the information about what quantum state you have there. And she also creates this random, if you know what it is, a random BB84 states, which are just random 0-1 plus-minus state, and she permutes everything. So it will be, this state is what we call trap qubits. And the idea is that she will mix this encoded state with these trap qubits and permute all of them. And when Bob knows all the private information, so the idea is that everything that Alice did here is reversible. So Bob can just undo the permutation, undo this quantum one-time pad, and check the trap qubits. So Bob has full information what he should be receiving. And the key point is that you can use this idea to, all these techniques or all these tools to show that the straps prevent any malicious party in the middle to heavily disturb the quantum state. And the error correction here will help us to provide this light one. So the idea is that these two have to work together. So just the traps are not enough to certify authentication. And the error correction here is just to prevent small modification on the quantum state. As I said, this is just a warm-up. Everything here also works classically if you think about random strings and a classical error correcting code. So this is not new. It's just, as I said, an example of how this quantizes. But now, let me switch gears and talk about some things that are more interesting, which is quantum secret sharing. And for those who don't know what secret sharing is, I think she might talk a bit about it, but let me briefly present it. In secret sharing, we have a trusted dealer that she wants to share a given quantum state among multiple parties. So she, based on this quantum state rho, she gives shares of states sigma I to, for example, here 8 parties. And what we want is that up to k colluding parties cannot retrieve the original state rho. But if you have k prime colluding parties, they can retrieve the quantum state rho. So it's a secret sharing of a quantum state. Okay. And as Chinmay mentioned, if you can correct up to some t errors, then it turns out that the density matrix on t qubits is independent of the encoded states. One can show that if it was if it was dependent, somehow you can distinguish quantum states, so you'd be collapsing them, and this would violate no-cloning theorem. And therefore, people realized in '99 that these quantum wire correcting codes, they are good enough quantum secret sharing schemes. And the idea is just the dealer encodes with quantum wire correction and send qubits to everybody. And this directly gives some sort of secret sharing scheme. But okay, what I want to talk more about today is that actually we can go one step further. And not only quantum wire correcting codes, they have this property that are secret sharing, but you can also, this property also holds if you apply local operations on these quantum wire correcting codes. So the idea is that not only we can, like local parts of quantum correcting code are the same, like they're independent of the encoded of the message, of the quantum message, but also operations on them are also independent. And this was a very key tool that we needed to prove zero-knowledge protocols for proof systems, and later to QMA. So this is the quantum version of the like the celebrated result that introduced zero-knowledge proofs in multi-prover interactive proof system. And this is the quantum version of the Sigma protocol for like a zero-knowledge protocol for tricoloring, for those who are familiar with that. So I'd like just to zoom in a bit how we used to prove the error correcting codes to prove this result.
A quick question. In secret sharing, you require also that usually if there are enough people, then they can recover the secret by the same token. Would that be impossible?
No.
Because, you know, if you have T, you shouldn't be able to tell anything. One more in threshold secret sharing.
Oh, so it won't be T plus 1. There are some K and K prime, such that up to K you cannot, and starting from K prime you can. So if you can correct up to T errors, if I give you n minus T qubits, you can recover the rest and you can decode.
But then if you can decode with any sufficient number by no cloning, wouldn't that mean that?
No, the point is this number has to be at least n/2.
Yeah.
And then you're done. Okay. Yeah. There's this thing. One of the bounds, like you need at least n/2 parties to be able to decode. Okay. So yeah, let me zoom in a bit how we use the technical tool that allowed us to prove like the simple zero-knowledge protocols for QMA. And by the way, QMA is just the quantum version of NP. So just think about NP, but where everything is quantum, the quantum proof, a quantum verification, and so on. And the way that you prove this zero-knowledge protocol for QMA was studying this problem called consistency of local density matrices. And this is what some people call the quantum marginal problem. So the problem that we have here is, suppose that you're given a description of pieces of a quantum state. So we have a classical description of a bunch of parts of the quantum state. And your question is there a global quantum state that's consistent with all of these parties, all of these parts? Okay, so what you want the input to the problem is just the classical description of reduced density matrices. And as I said, is there a quantum state such that this global quantum state is consistent with the local parties, or there are at least one of these parts that is rather far from all quantum states. And Yikai Liu proved in 2006 that this problem is contained in the quantum version of NP. And he also shows some sort of QMA harness for it, but only with 2 reductions. But the problem is, 2 reductions are not good enough, for example, for having zero-knowledge protocols. And this is the step that, like Anne Broadbent and I, we took to be able to prove this zero-knowledge protocol, is showing the QMA harness of this problem under CARP reductions. And this, okay, I don't have time. So the idea is that this, to proving this result, we heavily use some properties of quantum error correction. Let me just finish with, there are many other applications of quantum codes or classical and quantum codes in quantum cryptography. And let me finish with that. Oops.
Do a quick question while the next speaker sets up. There are no questions? Oh, no, there are questions.
In the secret sharing algorithm, like only one person can reconstruct the secret.
Sorry?
So in secret sharing, like only one, like, so even if the 3 of us split it up, 2 people put it together, only one person gets the state at the end.
Oh, yes.
And how does that, in the class, it's of course different in the classical case, within the group who shared, we all get the state. How does that affect other parts of protocols?
Now I think it will depend how the protocol is composable. So I think this definition is that everybody sends the shares together to someone, and this person has the quantum state, and that's it.
Yeah. So there's some protocols where, like, in a second round, other people would want to use, and now they can't because there's only one quantum state.
Yeah, there is just one quantum state.
Okay.
This comes from no cloning.
Yeah, clearly.
Maybe we can take the further questions offline, and let's thank Alex again. So our next speaker is Gabrielle Beck, who's going to tell us about apparently a single new direction for applying error correcting code techniques to crypto.
Sorry, thanks. Yes, I realized that my title was too broad. This talk will probably be a little bit more informal than the last one. I'm not going to. Oh, yes, thank you so much. Sorry. I don't know why I'm holding this. Can you hear me okay? Can you hear me all right? Okay, cool, thanks, sorry. This talk is gonna be a little bit more informal than the last one. I'm not gonna spam you with a bunch of math, but I'm gonna basically introduce sort of the new problem setting in which codes seem to be like a useful tool, and then we'll end sort of with a bunch of like open questions that I would actually like prefer a lot of help from people in here on. Okay, so right, so I'm going to talk about one new direction for applying error coding techniques to cryptography. And the main setting I'm going to be concerned with here is a relatively new technology, which I'm going to call like tracking tags or tags. And so what a tracking tag is it's actually just a low power and cheap device that will let you track belongings. So this includes things like you could put them on your luggage, on bikes, on like a car, those sorts of things. And tracking tags are made currently by a bunch of different companies. So this includes Tile, Apple, and Samsung. They look something like this. The most popular thing that you may, oh my gosh, sorry, that was a mistake. Okay, the most popular one of these is probably the AirTag, which is the one in the upper left corner here. And so tracking tags are interesting for a lot of reasons, but one of the main ones is because they're so low power, they don't have access to a lot of functionality, which means they don't have like a GPS inside of them. They don't have the ability to connect to the internet. All they have is basically they communicate with other devices over Bluetooth. So like very like near communication is the only thing that they're capable of doing. And so like, this seems kind of weird, right? Because I just said you can use these things to basically track items, but they also can't communicate with the original owner. So like, what is actually going on here? Well, when you purchase like some kind of tracking tag and you put it like on like a device and you step away from it, what actually happens is this device does the only thing it knows how to do, which is it begins sort of broadcasting packets locally. And there's a bunch of devices that are a part of what is called a volunteer network, which are listening for these signals. And this volunteer network is basically owned by the person who makes the tracking tags. So these broadcasts get sent out, the volunteers collect them. These volunteers will then form location reports based upon the broadcasts and along with location data that these devices have, upload it to some central server, and then you as the owner of the tag will communicate with the central server to get the reports. So that's basically how, at a very high level, you can use these devices to track things. Okay, so this is all well and good, but as a cryptographer, as a security and privacy person, typically when I see systems like this or proposals for things like this, I ask, okay, what can go wrong? Are there any sorts of privacy concerns that might exist in these sorts of systems? And there are two main ones that come to mind. One of them is potentially a tracking risk. So the way that this works is, say I have put this tag on a bike. I'm, riding around a campus somewhere. Maybe I step away from the tag, it starts emitting broadcasts. I then get on my bike, go somewhere else, step away, and then more broadcasts are emitted. If parties can link these two things together, that's kind of bad, right? Because you've learned some non-trivial information on me, and over time, you can lose a lot of privacy this way. So we don't want it to be possible for honest tag users to be tracked by anyone out in the wild. And then one other major concern here that I'm sure a lot of people have probably thought about, maybe in this context, is that, basically there seems to be a pretty big stalking concern. That is, there could be a malicious, tag user who doesn't use tags to track objects, but instead uses them to track people. And we would like to prevent this. At the very least, what we would like is for the parties who are being tracked to somehow be able to notice that they're being tracked, and then have steps taken so that they can do so that they can identify the tag and recover it or something. And this last one has many sort of real examples, and it's kind of a really big problem. So in these location tracking networks, I'm going to say there are two things we would really like. First, we would like to come up with constructions of those tracking networks that have privacy for honest users, but also somehow provide protection against stalkers. And this seems kind of difficult, right? For an obvious reason. So stalking victims really would like to tell when they have seen multiple broadcasts from the same tag. But that's exactly the tracking adversary, right? I just told you that we don't want it to be the case that if I see, this is a privacy concern basically for honest users if you can link together broadcasts from the same tag. So we're gonna take advantage maybe of a slightly strange assumption. So imagine I have a tracking tag and I place it on you. If I do that within any given fixed window of time, you're going to see most of the broadcasts probably that are made by the tracking tag, right? Because the only reason you wouldn't is if there's some kind of hardware failure. You will always be in that Bluetooth communication range. So most of the broadcasts are going to be seen by a stalking victim. However, we're going to make the assumption here that the tracking adversary has a much more limited window of view. And what this means is basically we can come up with systems where if you see a majority of the broadcasts, you can do recovery. But if you only see a small subsection, then that person or that tag is completely private. So that's what we're going to use. So this has a formal cryptographic definition that's actually kind of based on secret sharing, which was discussed earlier, but I'm only going to define this really loosely right now because I'm sure I don't have enough time. But yeah, so basically the main thing we want to do is construct a pair of algorithms, one of which produces all those broadcasts, which I showed earlier. And then another algorithm that will basically allow us to do detection if you get a list of broadcasts. So those are the two ingredients we need. And we want particular properties of these algorithms. So first one, loosely stated, is about the detection algorithm. So if a single tag supplies at least some number of broadcasts, we want it to be detected with high probability, whatever that means. It could mean I get an identifier for the tag or something else, but it should be detectable. And the second thing we want is that for a set of at most K broadcasts from a single tag, those should be unlinkable. And that's like the privacy property I was talking about earlier. What it essentially means is that, if I only give you like 3, let's say, broadcasts from this one particular device, it should be indistinguishable from if I gave you all from another device, or even like some other distribution of secrets from another party. Like all of these things should be indistinguishable at a high level. You shouldn't be able to tell anything about the distribution of those K values. Okay. Right, so, like from a really high level perspective, like if you sit here and like maybe you stare at it for a long time, it seems like this is a really good like setting for some sort of like coding theory problem, right? Because if we look at a fixed window of time, all of these parties are producing about the same number of broadcasts, and this like all of these tags are producing about the same number of broadcasts, and then we have a single party who gets some collection of symbols from those parties. So like maybe you can imagine each of these parties is like outputting a code word that is consists of a bunch of symbols, and the bottom party is getting some symbols from those code words and has to do like some list decoding algorithm or something to do recovery. So this is like, so this is like a good way to think about it maybe. However, like if you try to think about sort of the unlinkability property that we need, and in terms of a lot of existing code constructions, it seems like there's a lot of tension between these two ideas. Like a lot of simple things that you might attempt to do won't exactly work because you'll be violating the unlinkability property. So this is not to say that we can't come up with things. It's just that like you have to be like very careful on how you do things. And also as cryptographers, we don't usually think about things from this perspective. So like it's sort of an open question right now, like even what unlinkability means sort of in a coding theory sense. But yeah, so I guess what I'm just trying to impress is like there is a way to view this from that perspective, but I can only tell you the perspective that I know, which is not this one entirely. Sorry. Basically, within, how much time do I have left, by the way?
About 30 seconds.
Okay, yes. All right, so I knew this would happen. Okay, so basically within our work, we do show that actually you can achieve this unlinkability property from like a family of types of Reed-Solomon codes. So basically you have every single tag, choose a random polynomial of some given degree, and output like random, like evaluations at random points along with the X coordinate. And this is good enough for unlinkability. You can do this also with IRS code, so interleaved Reed-Solomon, where all of these polynomials are independent as well. These constructions will satisfy unlinkability. To do recovery, you need to do some kind of list decoding algorithm. So you can use standard list decoding algorithms for this. The only problem is basically for our scheme, like the parameters T and K, which I was talking about earlier, the privacy and recovery parameters, those kind of depend on the fraction of errors the code can correct from. And in an ideal world, you would want privacy to be as high as possible and like the detection to be as close to that as possible. And what this would really imply is that you need to be able to list decode up to capacity for these things. So, right, so we come up with a construction based on Guruswamy-Sudan, but it's like, it's okay for the parameters that we want. And because we showed earlier that IRS codes also satisfy unlinkability, if we had a good decoder for that, we can do potentially better. And that's also what this second bullet point is here. There's question marks in there because I am not sure if this is even a new algorithm. This is also one that can only recover heuristically. That bound, we know like better than that bound for other types of codes. And for IRS codes, you can like somewhat meet that bound for random errors. So this is like that bullet point's doing a lot of heavy lifting. And we show basically that our constructions are also efficient. So I think I went way, way over, but I have a lot of questions basically about like the kind of work that we did regarding this project. I don't have the time, I think, to explain what any of these are, but if you if you want to talk to me about this afterwards, that would be greatly appreciated. So apologies.
Yeah, so maybe in the interest of time, I see there are some questions. Maybe we can take them offline just to keep it moving. Yeah, so the next speaker can.
So hi.
All right.
Cool.
So next up we have Crystal Moen.
Moen.
Moen. Yeah, sorry.
Morning, but
We have Crystal Moen telling us about isogenies.
Yeah. Sorry, this has nothing to do with our correcting codes. I just saw a form that said, "Hey, sign up for a talk." So, thank you so much for bearing with me. And yeah, so I'm here because this workshop has a lot of things that I like, the computer science and math and number theory and graph theory. And isogenies actually has a lot of these things. So first, what is isogeny? We have to talk about elliptic curves first. So an elliptic curve is usually, unlike the previous talk, I apologize for math. So they have genus 1 elliptic curves with a specified base point, and each such curve is written as the locus of p squared over a cubic equation. When I say cubic equation, I mean y squared equals x cubed plus yada yada. And then there's usually a line at infinity. So when scaled appropriately, elliptic curve has a cubic polynomial form, which is expressed in this Weierstrass equation. So we go from this form on the top to this form, which is a Weierstrass equation. And usually the shortcut for it, the shorter Weierstrass equation is expressed as y squared equals x cubed plus ax plus b. So when we say genus 1, this is kind of a meme on the internet. So genus 1, 1 hole, genus 2, 2 holes, etc. A topologist's morning routine. And when we say a base point, we usually mean that we have this O equals 0, 1, 0. So at some point, our curve goes to infinity. And so it means that it's parallel to the y-axis, which is usually a characteristic of elliptic curves. And so when we draw elliptic curves, there's usually some point, even though we can't see it here, that goes to infinity. And there are generally 2 types of elliptic curves, the cusp type and the node type as well. So how do we make isogeny some of these things? So we have a pairing. An isogeny is a pairing group that is defined as a projective map between this genus 1, which we spoke about, the 1 hole, from E to E prime. So it has to be surjective, have a finite kernel, and is a group homomorphism, and has an elliptic curve defined on this short Weierstrass equation that we spoke about. So there's also a dual isogeny, which means that we have a homomorphism in the opposite direction. So we have one going to and one going from, so that we have a map called phi from E1 to E2. That is a non-constant isogeny of degree m. And then there's a unique isogeny phi prime that's going from E2 to E1. So this gives us these properties so that we get this separable M map, which allows us to prove a bijection, which we identify this bijection using something called Velu's formula. And so isogenies start from this elliptic curve of supersingular, which is usually denoted E sub 0. And then we get this elliptic curve pairing, which generates this large random expander graph. It's called a expander graph of Ramanujan properties. So these properties make a walk along a path appear random to an onlooker. And supposedly, according to the mathematicians, this makes our encryption, isogeny-based encryption, quantum safe. So what does isogeny-based encryption into sort of protocol look like? I will show a picture of Diffie-Hellman. So this is a classical Diffie-Hellman in which Alice switches A picks a secret integer that she doesn't reveal to anyone, and so does Bob. So we call these A and B. And then Alice sends to Bob the computed value of this function, which is g to the power of A mod P, and Bob does the same. And then we represent where they can identify that they sent the correct message to each other by this commutative diagram. So g to the power of AB should be the same as g to the BA. So when we try to do this with elliptic curves, we find that we can't actually do this. So what we have to do instead is we use this from the E sub 0, which is our starting curve. We create this isogeny, which is generated by computing phi sub 1 from the image curve of E sub 1, which is our Alice computation. And then we have an isogeny from E sub 2, and as well as phi sub 1 P2 and phi sub 1 Q2, which are actually shown here, which are the basis of the torsions of that E sub 0. And then we send the information. So Alice sends her information to Bob, and Bob sends the information to Alice. And so Alice computes this corresponding isogeny upon receiving this corresponding P and Q from Bob. And he computes his part, and then they look at their corresponding isogenies, phi 1, 1, just this one, and phi 1, 2. And then based on that, there's something that's calculated called a J invariance, and that's where you get the commutative property. So these two, J12 and J21, should be the same. So why would anyone want to make cryptography out of these things? They seem really convoluted. So in 2017, NIST started this post-quantum standardization, and isogenies actually survived 3 rounds of scrutiny and testing. Unfortunately, they didn't really go that much further. So there are these recent attacks that happened in 2022, and actually somebody asked me, so Gabrielle asked me about this before I give the talk. I actually have a sticker on my laptop that has it's like those tombstones that has the starting date of the isogenies and the ending date, 2022. And so there are 2 recent attacks that happened in 2022. These are the papers by Kashik and DeCreux and Damien Robert that talk about how they're able to basically break it within 4 to 6 minutes and 8 hours, 15 minutes, 20 hours, 37 minutes, respectively, on a laptop, which is pretty bad, right? So what does that mean for isogenies? Well, it is to be noted that the attack is on SID, which is the one that I showed, not Seaside. And there's also another protocol called SkiSign that's also safe. So not all of isogenies is broken. There's just some parts of the protocol that need to be fixed. That being said, I think there's also another hash function that's called the Charles-Gorenlotter hash function. And what the problem with both of these protocols is that you need someone to start the vertex. So we spoke about having a trusted party. Both protocols rely on this trusted party who has information about the kernel, extra auxiliary information, essentially. And with that information, it's possible that an adversary can break the protocol. So that being said, this is a similar hash function that has also been broken that needs to be fixed, and it relies on expander graphs. So I just wanted to say that part of my being here is that when I first started in 2022 with my advisors, Christelle, who's in mathematics, and my advisor, Joe, I was very skeptical about the whole expander graphs and post-quantum cryptography thing. And I think that there's a lot more information that could be learned, particularly because, so this is my PCMI t-shirt from 2022. The theme was quantum computing, and the year before that, it was computational number theory. In 2022, all of the mathematicians showed up to go to computational number theory. So I knew everyone there. And then in 2023, about 4 of us showed up. So there's something that's not happening between people making post-quantum cryptography and people working in quantum computing. And so I'm here because I think there's a lot that can be learned by those 2 communities coming together, especially if we're on the mathematics side talking about hardness properties theoretically, and the quantum people are saying, well, we don't quite agree with your so that's kind of why I'm here, and yeah, thanks.
One quick question while the next speaker sets up. No questions. I guess let's thank Crystal again.
while I set up, I guess I can already comment that there does seem to be a bit of a, a crypto theme to the last few talks. So if that does interest you, there is a crypto reading group. So please look out for that on Zulip. I'm currently soliciting, feedback on what the best time to do it would be. So, anyways, let's start this up here. Thanks. Think I'm spoiling.
While you set up, I can introduce you. Next up, we have Nick Gresh from the University of Amsterdam, who may or may not have slides.
There we go. Well, I don't have slides. In fact, what I did was I wrote some stuff down on my iPad. I was planning to, just write it on the board. Then I realized, wait, what's the point? I can just do this. So, So the plan is to talk about a topic that I've recently gotten interested in called smoothing codes. And I think it's kind of a nice topic for a coding theory audience because it might not be a problem that you've looked at before. But first of all, it might have some connections to some stuff that I guess Henry and I have been talking about, or proving that Reed-Muller codes achieve, this sort of threshold phenomenon. Somehow the point at which you get close to 1 is kind of related to the point at which you smooth the code. And also it's, pretty easy to understand the problem. So hopefully I can explain it in the 10 or so minutes I have. Okay, so what is the basic idea? So I give you some code C and some sort of error distribution, E. So you can just think of this as some sort of, like a random vector. And what I want to be able to prove to you is that, if I take a random code word and add, some noise to it, according to this error distribution, I want this thing to look roughly uniform, right? This is my cryptographer's notation, so forgive me if you don't like it, but this just denotes the uniformly random code word. Another way to perhaps say this, if you prefer, is I could just imagine looking at my error distribution and modding out by the code, and I just want to, argue that this is uniform. Okay. And, if you want to be precise, let's say, I want to prove that in the total variation distance or statistical distance, whatever you like to call it, 1/2 times BL1 norm, it's very, very small. Okay, don't worry too much about the precise quantification. Good so far? I guess I don't have a lot of time, but I think it's still nice to solicit questions.
Of course, bounded adversaries. Like, is it computational?
There's no adversary at the moment. Yeah, everything is just, I just have 2 distributions. Yeah. Good. Okay, so what is sort of the question here? Okay, wait, let me see. What's the motivation here? First things first. So why am I interested in this? Well, to some extent, it's in order to create, it's a natural avenue towards proving a worst case to average case reduction. So what am I talking about here? So we can imagine sort of a worst case decoding problem, which I'll call WDP with, these 3 parameters, N, K, and W. And I guess throughout the talk, I always get confused whenever I have matrices and vectors, so I like to draw them as shapes, so I keep track of what the right dimensions are. So what is my input here? You could just think of it as like a generator matrix and then some target vector Y. And, it's the decoding problem, right? So, you imagine you're Bob. You and Alice agreed that you're going to use the generator matrix G to encode your message. And you're Bob and you receive this vector Y. So the problem is first of all, that your channel wasn't too mean. So basically, your vector Y is at most, Hamming distance W from some genuine code word, which is, always of the form generator matrix times the message. And your goal is just to recover the message, or actually equivalently, if you like, if you recover the error, that's also sufficient because then you just subtract the error off from the Y that you received, and then you can invert the matrix to find the message M. Fair enough? This is nothing fancy. This is the classic problem. Of course, for worst case matrices, we already know back from 1978 or so. I don't want to say too much about this because I'm afraid I might say something that might be false depending on the exact parameters. But broadly speaking, this is a very hard problem and even NP hard, for most parameter regimes. Good. But now, of course, for cryptography, the hardness of a worst case problem doesn't actually buy you anything because in cryptography, the first thing you need to do is randomly sample a key. And so there's already some randomness involved, and then you sort of naturally will create average case problems. So you need actually that your problem is hard even if your inputs are randomly sampled. So even if we all agree it's hard to solve decoding in the worst case, we still want to be convinced that this is hard to solve also in the average case. And well, okay, there's a lot of people who have tried to solve this problem over the years. There's I think there are even some like scoreboards up, you can actually look up online to see what are the biggest decoding problems that people have managed to solve so far. But, maybe here I'd like to give some sort of theoretical evidence that this problem is indeed hard. And somehow when you deal with this average case problem, it's quite nice to switch to this oracle-based problem called learning parity with noise. And how is this one usually described? Well, here we have some sort of fixed oracle that is given to us, and kind of embedded in this oracle is some secret vector S. Okay, and this vector S has length k. And what I'd like to essentially do in the end is determine this secret vector. But the oracle is somewhat unreliable. So whenever I ask it for, whenever I press a button, say, the oracle will talk to me, and it will tell me, first of all, some random vector A, and then it'll give me the inner product of A with the secret S, which is great. But it also, of course, maybe with probability P or probability, let's say 0.1, it'll flip the output on me. Okay, so this addition is modulo 2. Let's say for simplicity. Okay, so this is basically. You could imagine, say if I take, n samples from my oracle and I stack them up into a matrix, this would just generate a uniformly random matrix. And then, if I look at all of everything I receive, that would and stack them up, that would give me a vector y. So this is basically an average case version of the decoding problem. The only real subtle difference is that the rate or whatever of the problem is not fixed a priori. I can keep on asking for more and more samples that I want, say within polynomials time, but morally, it's a nice problem to look at. Okay. Everything clear so far? Cool. I probably should have checked the time before I started, but hopefully about 5 minutes. Okay, good. So keep that in mind. So what would I love to prove? Would be something like, suppose that the worst case decoding problem is hard, then so is the learning parity with noise problem. And to make this interesting, the challenge would be that I would like to, start from, in some sense, the most conservative assumption possible. So for the, if the target decoding radius that I'm aiming for is W, this problem gets harder and harder the larger W is. Of course, if W equals 1, I can solve this problem in, linear time. I just try flipping each bit and seeing which one is correct. But, once W is super polylogarithmic, let's say super logarithmic, I guess, log squared n, let's say, that's already, to the best of our knowledge, cannot be solved in polynomial time. But anyways, making W bigger and bigger means that I'm making a more conservative assumption, like I'm assuming a harder problem is indeed hard. And then I'd like to prove that, some other problem is hard. And I'd like to, prove that the conceptually easiest problem possible is hard, right? So if I make P really small, as P gets smaller, it should be easier and easier to solve this LPN problem. So, from a cryptographer's perspective, if I want to, have a hard problem, I want the seemingly, easiest problem possible to be hard. Okay? So that's what we want. Now, how could we do this? There's a very natural reduction coming from, I guess, the work by Brekkersky, Lubashevsky, Vaikuntanatan, and Daniel Wicks. This was in 2019. It might have been around before, but it's a very natural thing to do. So what I want to do, I need to create, some sort of reduction. So I want to solve the worst case decoding problem with the assumption that I have some sort of algorithm that, say, I have black box Oracle access to that solves the LPN problem. Okay. So what any reasonable reduction will start off by saying, okay, run this algorithm A. And then, of course, this algorithm A is going to run along. And at some point, it's going to want to press its button and ask for an oracle. Ask its oracle what, for a transmission or whatever. So I'll note this by, this sort of question mark here. And now how should I respond as, as the one who wants to solve this worst case decoding problem? Well, what I'm first going to do is sample some vector R according to what I'm going to call a smoothing distribution. So it'll be clear in a second what this smoothing distribution should be. And then I need to respond by, sending back, a vector of length k and just like a single bit. Okay. And the vector of length k, well, I've set things up nicely. So if I do sort of this I guess I need to multiply from the left here. So I'll end up with a vector of length k when I do R times G. And this is sort of morally like my the vector A, sort of that we expect from this LPN sample here. Okay. And now to generate sort of this other bit here, I'm just going to output the dot product of R and Y. Okay. And where again, Y is like the vector that I'm trying to decode. So why is this a good idea? Well, if we break up Y based on our assumption, it's of the form, some sort of code word plus some noise vector V here. And, associativity, I can move things around, or I guess, no, I'm not using associativity. I'm using distributivity. Oh yeah, and associativity here. Anyways, so I can regroup it so that this part here is indeed exactly the thing that I called A above here, right? So this looks like A, and now, in one case, I want to recover the message M. This is basically like the secret S for my LPN sample. And now R.V here, well, this is just some bit. Okay, so this essentially looks like an LPN sample. There's some issues here. Like, first of all, it's not like usually with LPN, you need that the bit B is independent from the sampling of A. But if you look at it here, they both depend on the same underlying vector R. So, okay, this independence might not exist. In practice, that's usually not the big problem. The main requirement that we have to hit is that we need this first thing to look uniform, right? Because the only guarantee I have is that this algorithm A solves LPN, and the LPN is, the LPN problem is stated in such a way that these vectors A are already sampled uniformly at random. So I need this part to look very uniform. Okay, but in order to, if you think about, how is this bit B here distributed? Well, V is a sparse vector. And well, if R is like usually pretty sparse, then, dot product of two sparse vectors is usually, pretty close, biased towards 0. So I want to make R as sparse as possible so that P is small. And now, okay, so this is what we want. I'm running out of time, so I won't say too much more. But basically, so in this work, I guess with Thomas Deby, Léo Ducas, and Jean-Pierre Tillich, we sort of studied these kind of smoothing bounds abstractly. And in fact, if you have, well, for random linear code, basically, you can get sort of optimal smoothing bounds in the sense that you basically, the amount of sort of entropy that your sample needs is roughly n minus k bits of entropy, which is sort of optimal since I need to, E modulo my code, which is, distributed over n minus k bits. That should look uniformly random. This is sort of a statement that holds with high probability over random codes. And the proof is basically just not worth getting into. And we can also then talk about NKD codes. And the main sort of thing I want to leave you with is that, well, we can sort of plug this in. And unfortunately, we can't actually really get any sort of improvements over previous results. And the previous results are actually very disappointing. So basically, in this sort of reduction, we're able to show that, say it's hard to decode like log squared n errors, which perhaps you agree with me is like technically not solvable in polynomial time. Like, you can try your favorite algorithm and it will I think the best you can do is probably 2 to the log squared n time. Okay, so it's not solvable in polynomial time. Then we can conclude that sort of, I threw in some numbers. I think these are essentially correct. You can't solve this version of LPN. And technically, since I have an inverse polynomial gap from 1/2, this is solvable in with polynomially many samples. But of course, I don't think anyone believes that this, like from my perspective, I would say this problem is way easier to solve than this problem. So, I proved that a seemingly easy problem is, if a seemingly easy problem is hard, then a seemingly hard problem is also hard. So it's a bit unsatisfying, I would say. And yeah, maybe I'll just leave sort of with the question. Maybe it's actually impossible to do better with this sort of reduction. And this would sort of imply that. So anyways, I'll maybe stop here.
Maybe in the interest of time, we can take questions offline. Okay, so last up, but certainly not least, we have Roni Khan to tell us about Reed-Solomon codes versus deletions, the epic battle. Sorry, I guess it doesn't say that on the slide. I assume that was.
Can do that. So, hi, I'm Roni. I'm currently at
the Technion. I just did my PhD with Amir Shpilka and Tzachi Tamo in Tel Aviv University, and I'm a postdoc now at Technion, working with Eitan Yacobi. And I'm going to talk about Reed-Solomon code versus deletions. And I'm going to jump right ahead to the picture that basically tells us what linear codes can do against deletions. Okay, so jumping to the broader picture of linear codes in general, not only Reed-Solomon code. So, okay. So, Chen Guruswamy, Hauptler, and Lee recently basically initiated this research saying that there are good linear codes that can correct deletions. And by good, I mean that if you pick a matrix, a generating matrix at random, then it can correct delta fraction of insertions and deletions. And let me just say just deletions for this talk. So it can correct delta fraction of deletions and have this rate, which is 1 minus delta over 2 minus this thing. And they showed also two upper bounds. The first upper bound called half-Plotkin bound, saying that basically you cannot do much better than this. Okay, you're bounded by this term. But what we'll be focusing on today, it's the half-singleton bound, which is just taking the alphabet dependency out of here, basically saying that if you have a linear code, the best you can hope is that your rate is going to be half 1 minus delta. And this is the half-singleton bound. This is in contrast to nonlinear codes. Nonlinear codes achieve the singleton bound. There's construction by Hauptler and Sharabi. So, yeah, linear codes are provably not as good as nonlinear codes in this setting. And just a quick remark, it's not a rate distance trade-off, it's a rate error correction capability trade-off, okay? This is because basically the eddy distance metric is from 0 to 2. Okay, so basically when I say like this inequality, I mean that a code can correct delta fraction of deletions. Can correct, not of a distance. So what about Reed-Solomon code against insertions and deletions? Good, so we've seen Reed-Solomon code a lot in this, right? In this bootcamp. This is the definition. And also we can describe Reed-Solomon code using the generating matrix, which is the Vandermonde matrix. I write it this way, though people write it the other way around. And right, you take a message, you multiply by the Vandermonde matrix, and this is equivalent to evaluating a degree at most k minus 1 on alpha n up to alpha points. And these are the points that basically define a Reed-Solomon code. When I say Reed-Solomon code, I mean, tell me the points. We love Reed-Solomon code. I mean, yeah, we love. Not just we in this room, but the entire world loves the Reed-Solomon code. This is from Essential Coding Theory, okay, the greatest code of them all. And, well, a lot of reasons, all of us know about these reasons, so I don't need this motivating slide, basically. But let's focus on deletions. And let's take a closer look into a special case, k equals 2. K equals 2, we are looking just lines. Okay, our polynomials are lines. And we have this evaluation on a line. And if I want to tell you, okay, tell me the polynomial, you basically need two pairs, right? Alpha I, f of alpha I, alpha j, and f of alpha j. But in this work, I'm giving you this information. I'm giving you 3 evaluations, f of alpha I, f of alpha j, and f of alpha s, without telling you the points alpha I, alpha j, and alpha s. Okay, I just tell you that, okay, so they are ordered. They come, I mean, they preserve the order from the code word. This is the only information, and I tell you, learn F, or reconstruct it. And so this is possible. Okay, and there are a couple of works about it. So this old table describes Reed-Solomon code. Dimension is 2. They can correct n minus 3 deletions. So the single parameter that can, vary is just q, the alphabet size. So we started, Duke et al. Started and showed the construction where q is exponential in n. Then together with Amir and Tzachi, we showed a construction of where Q is n to the 4, and we also showed a lower bound of n to the 3, namely every Reed-Solomon code that can correct n minus 3 deletion two-dimensional must have this field size. Chronologically, after our work, there's also this work that constructed a different code of field size n to the 5. And recently, we closed this. So for the k equals 2 case. What about larger k? Situation here is not that good. I'm personally aware of only one work that studied it before that showed a code that can correct this number of deletions, a very small number, but the field size is very small also. It's not, I mean, it's generalized Reed-Solomon code. And in the same work, we showed two things. We showed an existence, namely there are Reed-Solomon codes that can correct from this amount of deletions with this alphabet size. And also we constructed a Reed-Solomon code over much larger, higher field. This is n to the k to the k. It can correct the same number of deletions. And why this particular number matches the half-singleton bound. Okay, so we're interested in showing that Reed-Solomon codes, there are Reed-Solomon codes that are optimal. Achieve what? The best. Yeah, so, yeah.
Is this also with decoding or efficient decoding? No.
It's purely information theory, showing that the code has edge distance.
Is k fixed here, or can it also be n over 10 or something?
What?
K can be like proportional to n in this, so we're thinking of k as fixed.
N can be proportional, but you know, even writing the points will take you exponential time. So. Okay, so yeah, it's not. There's a question over there. Yeah.
Do you also have a lower bound on the Q?
So it's funny. The lower bound for the k equals 2 case does not generalize nicely to the k greater than 2. And to be more precise, for k equals 3 degrades to, I think, 2.5. For k equals 4 to 2, and it slightly integrates. We eventually get, for larger k, we get a lower bound of 1. So, yeah.
That actually sounds like probably less tight as k.
Yeah. Yeah. It's a really not good lower bound. But only for only for this case, it's good. Yeah.
Are the evaluation points arbitrary here, or?
No, I mean. Okay. So here is an existence result. Evaluation points. There are some evaluation points, and here no. I tell you what are the evaluation points. So can I have? Do I have 2, 3 minutes?
Maybe 2 minutes.
2 minutes, great. So just say a few words about a condition that implies Reed-Solomon codes correcting deletion. So I'm looking at this huge matrix, which I like to call it a double Vandermonde matrix, because it has two parts, I part and J part, where I and J are basically increasing sequences of indices, okay, of length 2k minus 1. And so this is a definition of some matrix, and I'm having the following condition. I'm putting, instead of the formal variables, I'm putting alpha 1 up to alpha n. And then I'm looking at this matrix. This is a square matrix. And I'm claiming the following thing. If for every two increasing sequences, I and j, that agree on at most k minus 1, agree pairwise, like agree, it holds that this determinant is non-zero, then the code can correct n minus 2 k plus 1 deletions. And just to say a word about the proof, think that think of what an element in the kernel looks like. It looks like a polynomial f is equal to some polynomial g at some point alpha I equals alpha g. So f of alpha I equals g of alpha j1. Again, you can think that there are here a lot of agreements, and this is basically the LCS between two polynomials. Okay, so I want it not to exist. So if this determinant is non-zero for any such configuration of I and j, then I can say that any two distinct polynomials, the evaluation do not share an LCS of 2k minus 1 length. Great, open questions. So the construction is really bad. It's the best that we could come with, but it's really exponential like field size. So, and we know that you can do n to the k. So do it. A tighter lower bound, like these two things are basically the same question. What is the right field size for a Reed-Solomon code that achieves the half-singleton bound? Decoding algorithms, all of our codes do not come with a decoding algorithm. And it'll be super interesting. You know, you could try all the configurations, but exponential. And I don't know, maybe less decoding. All the things that you do with the Reed-Solomon in the classical setting, you could do with Reed-Solomon in the deletion setting. Thank you.
Do one quick question.
Do you think it helps to also go to like multiplicity kind of codes?
I don't know.
And derivative.
That's actually a good segue, speaking of open problems, into our next event, which is an open problem session. But first, let us thank Roni again. And let's thank all the speakers in the Speed Talk session. And more clapping. Let's thank all the speakers.